Hey everybody, I wrote this really fun song on bass that I want to share with you. Isn't that great? Isn't it cool that you can do that on a bass? Okay, moving on. No, actually, it's going to be extremely relevant to the topic, believe it or not. Not little lambs, but like frequencies and stuff. So, this is kicking off really the final topic of our semester already. Wow. And this is one of the more conceptually challenging topics that we do this semester. A lot of people do find this tough the first time they're learning it, second time for that matter. So do buckle in, get ready, and we are going to make this happen. We are looking at Fourier series, Fourier analysis, Fourier transforms, all that good stuff to close out the semester. And I want to start by going back to the basics, everyone's favorite topic, Taylor series, of course, and keeping in mind that Taylor series are just one option for the way that you can expand a function in terms of a sum of other functions. You can do polynomial series in general. So this, of course, is starting to look similar to the Taylor series expression. But you could say, yeah, I'm going to write my function as a sum of a bunch of different polynomials, some sort of x plus x squared plus x cubed plus so on, each with different coefficients in order to make things add up to the right quantities. So that's fine. We've been doing that all semester. People are even starting to say, like, yeah, I'm kind of used to this now. So given that, where do we go from here? We could ask, does it have to be polynomials? No, yeah, it has to be polynomials. That's it. We're done. Okay, lesson's over. Bye. No, just kidding. Okay. It's always tough to figure out how long those awkward pauses need to be. Anyway, there are many options for how to do expansions of a function in terms of other functions. And what we'll be exploring in this unit is working with periodic functions. So this is a very natural material science topic. There's lots of periodic stuff happening in materials because of crystals and lattices and, the symmetry of these structures. So what we're going to do is to, instead of building a function out of polynomial terms, we're going to build it out of sine and cosine components. And I'm using that word components very intentionally. Spoiler. Okay, that's the proposition anyway. And on the surface, I hope it does actually seem reasonable that if we're working with periodic functions, then saying that they must have some sort of sine and cosine content to them really should seem reasonable. The question of if it actually works is another question. So that's what we need to get into. Good news, all of our training in linear algebra is about to pay off. I mean, it already has been, but like even more so, because in the language of linear algebra, really we're addressing the question of, do the functions sine and cosine, do they form a basis for the space of periodic functions? You can absolutely talk about this space as a vector space, that you can have periodic functions and they have some components to them, and those components have different frequency content. So those are the n's in this expression. N can be any integer, 1, 2, 3, 4, 5. And if we add together the right amounts of the right different frequencies, then we can build any periodic function out of those combinations of sines and cosines with different frequencies. So what we're saying in linear algebra language is that the space of periodic functions is spanned by sine nx and cosine nx. That means that they form a basis for the space, and a linear combination of those basic functions can be used to build up any periodic function. So vectors are not just arrows pointed in certain directions, and they're not just lists of numbers. The concept really is much more general than that. And because we have our linear algebra tools, we can use all of the other power of linear algebra that has been developed this semester to explore how this works and to do different kinds of calculations and to do reasoning on how these things should behave. So we can talk about something like the inner product of two functions, which is where we're going next. We can talk about normalizing a function, doing some operation that will set its magnitude such that this operation gives you a value of 1. And like all of this language, all of these tools, this is all going to come into play here. Now, in order for these functions to form a basis, in order for sine and cosine, sine x, sine 2x, sine 3x, sine 4x, yada yada, in order for them to form a basis of all periodic functions, those basis functions have to be linearly independent of each other. What does that even mean? What does it mean for one function to be linearly independent of another function? Well, we're actually not going to do the full proof because, surprise, I know the answer already. But we're going to do a little bit of a workaround and figure out whether these things are orthogonal to each other. Because if they are orthogonal, then they must be linearly independent. So we're going to approach the problem from that point of view, is to try to do an orthogonality calculation. And you're like, okay, fine, but what does it mean for two functions to be at right angles to each other? Well, this is where I have to say be careful with your language. Orthogonal does not mean right angle. Orthogonal means the inner product is 0. That is the true meaning and definition of orthogonality. When we're talking about vectors that are arrows pointing in a certain direction in space, and that there are angles between those arrows, in that special case, orthogonal does mean right angle. But again, more broadly speaking, orthogonal is a statement about inner product. So if the inner product of these two functions is 0, they'll be orthogonal, and if they're all orthogonal to each other, then they must be linearly independent. So how do we do this? How do you calculate an inner product? Because when we learned to do inner products before, it was like x1, x2 plus y1, y2 plus z1, z2. It was this sum of terms over the components of the vectors. Well, now what? The vectors don't even have components, or do they? If they're continuous, well, go back to Calc 1 for a minute. If you have something that is a sum, but then you extend that sum to contain an infinite number of terms, we have a concept for this, and we have a calculational tool for doing this. It is, of course, the integral, right? That's a sum over an infinitely many number of infinitesimal little slices of something. So what we're going to do is we're going to take these functions, slice them up into a whole bunch of tiny little pieces, and then compute the products of each of those pieces pairwise, and then add them all together. Because that's exactly what you're doing in an inner product. It's just now we're going to have infinitely many of them, but that's no big deal because we know how to integrate. There is one little caveat here that I am going to draw your attention to, which is to remind you that these things can, in principle, be complex valued, and that when you are taking the inner product of two complex valued vectors, the first one, the one on the left, does get a complex conjugate applied to it. So that's the f star of x here that's saying the complex conjugate of the function f. Okay, so then if this is our inner product, which it is, there's no trick here, there's no trap, this is how you calculate the inner product of two functions on some interval. It's the integral of their product, which is analogous to the sums of all the corresponding products of finite dimensional vectors. Then orthogonality means inner product is 0. So let's try one out. Let's see if this works. I'm not going to do every possible sine and cosine, and I'm not going to do the general case. I just want to show you one example to give you the idea of how this looks. So what's the inner product of sine of x and cosine of x? Well, we set up the integral over one period. It makes sense to to have your interval be 1 period because that is the sort of natural symmetry of this function. And what I have here is I have put a graph of the product, sine x, cosine of x. So that way we don't even need to do the integral, because I don't remember which trig substitution to do to do the integral correctly. But we can just integrate it graphically. Like you look at this product and you say, oh yeah, sure enough, there's an equal amount of stuff above and below the axis. And so my positive and negative area contributions are equal and the total integral will be 0. So these two functions are in fact orthogonal to each other. And if you repeat this calculation more generally for sine of nx and cosine of mx and work out these possibilities for the different integers n and m, then you will in fact find that in most cases they are orthogonal to each other. So now you're like, wait, you just said most cases. I did say most cases. There is one case where the functions are not orthogonal, and that's when they are the same function. So without doing all the calculations and doing all the derivations and proving the things, not that there's anything wrong with that, I just don't think it's the best use of time for introducing the topic. What we're going to end up with is the ability to say, okay, I have all of these basis functions, I'm going to have sines and cosines, and that any function can be then written as a sum, maybe finite, maybe infinite, a sum of all of those basis functions, each one with a certain coefficient. This is the linear algebra of it. This is the linear combination of these functions, is 2 times one of them, plus 4 times another of them, plus -1 times another, plus, adding them all up linearly. The a0, an, and bn here are those coefficients. Those are the components of the function written in terms of these basis vectors. So we need a way to calculate what these coefficients are. The way that you find the components of vectors is to do inner products. This is what you've always been doing when you've been working with arrows that are, you know, like in your physics 1 class, and you say, yes, I have a force in this direction. What are its x and y components? And you're like, yeah, I remember this, f cos theta and f sine theta. But cos theta and sine theta, where did they come from? Those come from doing the inner product. If you have, so just for example here, like, yes, the x component of my force is f cosine of theta. Really what that is it is the dot product of the force vector with the x direction basis vector for your coordinates. That's really what you're calculating there. So in general, what we do to find any component of a vector is to take the inner product of the vector with that particular basis, the 3rd or 4th or 17th, whatever basis vector that we want that component. And since these coefficients, the an and the bn, those are the components of our function that we're trying to build up, all we have to do is calculate a bunch of inner products, which now you know how to do. You do integrals. So at this point, I am just going to write down the answer because I do want to get to the point of it all. While I'm not proving these things, I am trying to argue for why they're believable at the very least. So looking at these 3 formulas, let's break this down a little bit. Oh, geez, typos. Okay, so this should be cosine of nx, and this should be sine of nx. Sorry about that. My bad. All right, the first one, a0. If you look at this, this is the average value of the function itself. And if you think about like way back to pre-calculus when you were learning how to define trig functions and like make graphs of trig functions, you had this constant term out front, and that was the average value of the function, and then the sine or the cosine like oscillated around that average value. So that's what a naught is here, and you can see that it is the average as calculated using your calculus toolkit. So then the an, those are going to be the cosine frequency components of the function, and then the bn will be the sine frequency components of the function. And remember, it's cosine of nx, sine of nx. This is the inner product. This is the inner product of f with a basis vector. This is the inner product of f with a basis vector. Okay. We will have an example of this. I'll show you one all worked out in the next video. I will make this concrete. For now, I'm just laying out the ideas. There are a couple definitions that I need to put up here real quick. Here they are. This is going to be used for shorthand for sure. It's going to be used for expressing some of the answers in a nicer way. And the idea here is that in math, it is very useful to just ask the question, are these two things equal or not equal? And when we're writing out expressions, instead of having to do long written stuff of like, well, the formula is this when these two numbers are equal, but the formula is something else when the others are not equal, and then blah, 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 that just gets to be a lot of writing, and we like to condense things. So you can use these deltas, the Kronecker delta here, as almost like a logical operator in your mathematical expressions, that it just tests the question of, are these two numbers? So it takes two numbers as arguments, and then it just asks the question, are they the same or are they not? And if they're the same, it returns 1, and if they're not the same, it returns 0. Now with these subscripts here, that is suggestive of some kind of matrix, because you're like, well, if m and n can be numbers and I can count 1, 2, 3, 4, whatever, those could be rows and columns of a matrix. And yes, they absolutely could. And that is what the identity matrix looks like, right? It's zeros off the diagonal, zeros where the row and column are not the same number, but then it's ones on the diagonal where the row and the column are the same number. So we've actually seen this thing before, we just didn't express it in this very compact notation. So there's our Kronecker delta. This just says if two things are equal or if they are not equal. And that is a discrete operation. We take in two numbers, we compare them, we're done. But there's also continuous questions that we might want to ask of, if we have this continuous range of numbers and anywhere within that range, is something equal or is it not? This gives us the Dirac delta function. Apparently I am having a little bit of trouble with slide making on this topic. So this is the Dirac delta function, delta of x minus a, and this again acts kind of like a test. But this expression is going to be used in integral expressions. So what's going to happen is that we need to be set up, this is a very weird definition. I have function in quotes because some people are like, it's not even a function. It's a mathematical construct, it's a calculational tool, but it doesn't really meet the definition of a function like you learned in pre-calc or calculus. But it is something that we can write down the rules for it, and we can do calculations on those rules. So here are the rules. It is an infinitely tall, infinitely narrow spike. That's what the Dirac delta function looks like. Here's my f of x, here's my x, and at x equals a, exactly at that one point, it is an infinitely tall, narrow, infinitely narrow line. It is a vertical line with no width, but it is vertical with, I love saying this because it makes mathematicians rage. It's just exactly infinitely tall enough such that when you integrate it, the area under it is 1. So it's infinitely tall, infinitely narrow, but the product of its height and its width is 1. So I'm like, hey, 0 times infinity is 1, hooray. And then all the mathematicians chase me out of the building. It's really, I love it. So, um, you know, jokes aside, although that's not entirely a joke, but on the topic of the math itself, why is this useful? It's useful because sometimes we want to pick out one particular value of a function. We want to say, okay, here's my function, and it is defined in some way, like, here's a function. And I want to ask the question, what's the value right here? Well, the integral of f of x times the delta function centered here, so delta of x minus a, that is going to return f of a, because we're going to make a almost like an evil twin of this function that is 0, 0, 0, 0, 0, 0, 0, boop, right here it's not 0, 0, 0, 0, 0, 0, and grab out that one value right there. Why am I bringing this up now? This just seems like completely random. Sines, cosines, infinitely narrow spikes. That'll come up very soon, trust me. We got to build up the pieces here. Now, I've been talking about periodic functions, and that was the whole start of the argument. I was like, if you have a function that's periodic, it makes sense to build it out of sines and cosines. Does that mean that this series analysis, this Fourier series analysis, can only be used on periodic functions? And the answer is no, actually. We can extend it more broadly to other kinds of problems. What we need to do is to make some adjustments in order that the requirements for doing the math are met, that our assumptions about the linear algebra of the system are valid. So if your function is periodic and it is periodic on some other interval, then you can just fix that with a change of units. That's very, very easy to do. If your function is not periodic, then what you need to do is to create a periodic version of that function. I will show you how to do that. First, so just a reminder, here's our coefficient formulas. This is exactly the same slide as before, except this time I somehow managed to fix my n's. Good work, me. So here is our set of 3 equations for calculating the sine and cosine components of a periodic function with a period of 2 pi. In order to look at other functions that have other periods that are not 2 pi, you do a u substitution. This is the whole thing. I'm not going to belabor the point on this one. You've been doing u subs for a while now. Just do a u substitution. That'll change the units on your x-axis, and then everything is great. And you now have your integrals in terms of whatever the length of that function's period is. So that's that. I want to move on to the last topic for the day. This video is going to be a little longer. The next one's also going to be a little longer. It just has to be that way sometimes. What if our function is not periodic at all? How can we build it out of periodic components? Well, what you can do is you can periodically extend the function. You can create an extended version of it that is periodic, and then perform the analysis on that extended function. So here's how we do this. These are all the words that I just said. I got ahead of myself. Here's how we do this. I want to talk about guitar strings. I mean, who could possibly imagine why we might be talking about guitar strings in a case like this? But really what I want to do is to talk about frequency content. So just listen for a second, use your ears. If you're listening at higher speed, set it to 1x, listen to this at real speed so the pitches don't get messed up. Okay, so your video's at 1x, congratulations. just listen to these. I'm going to play the same note a bunch of times. Listen to how the note changes. Those are all the same basic frequency. That's a D. They all have the same fundamental speed of wiggling back and forth. But what's different about them is they all have different, what musicians call timbre. They have a different quality to the sound, even though the bum, bum, even though this is the same frequency, it's the same note, it doesn't change. But, you can play it so it sounds different. Why am I talking about this? Because we can explore this with Fourier analysis, and we can ask, what are the amounts, what are the components of all of the different frequencies that make up that note? And I'm connecting this to the periodic extension because I want to look at a function that looks like this. So what I have here is I have a guitar string. It goes from 0 to L, and I'm going to pluck or pick or whatever the string at a particular point. So what's going to happen is we are going to have an initial condition for the string where it has a displacement here, and it is, how do I want to say this? We're going to hit the string here, let it go, and let it vibrate back and forth. Then, to calculate what those vibrations are is incredibly difficult, and we're not going to do that problem. That would be like a whole project. It's actually very difficult. But what we can think about instead of solving the spatial problem is we can solve the frequency problem. You can ask, what are the frequency components of this initial condition? How much low frequency content does it have? How much high frequency content does it have? And that tells you how these things sound different. The difference between that note has more low frequency content. I'm hitting it in the middle of the string. And that note, I hit very close to the edge of the string. It has a lot more high frequency content. They have the same base frequency, but the components of that function's vector are different. And to find those frequencies, here's what you do. You can extend this initial condition in 3 different ways. One way you can do it is to simply make a version of it that repeats over and over. Like this. So you could just build this extended repeated function. So, 0, L, 2L, keep the period the same. And that's definitely a 3. And then you can take this and you can calculate its sine and cosine frequency components with this version. Or you can take this initial condition and you can make an even version of it. So remember, even functions are functions that are symmetric around the y-axis. Oh, okay, that was a little off. It is actually kind of important that I draw this somewhat well. There we go. Okay. And then I am going to create this mirror reflected version of the function over here. And then this is the even version of this function. And if I do this calculation, what I'll find is that it will only have cosine components because cosine is an even function. And so this extended function being even only has even frequency components. But you can also make an odd version of this. An odd means, remember, that it's symmetric around the origin. So like that. And if you calculate the Fourier series of this version of the function, you'll find that it has only sine components, that it'll all be odd frequency content. Whichever of these you use, you're choosing to solve the math in a different way. You are making a slightly different version of the problem. They're going to give you similar results, but one of them might be much easier to calculate than the others in terms of doing the math. Knowing which of them is going to work well, it's tricky to predict ahead of time. It's one of those make your best guess situations. But the whole reason I brought this up, besides, wanting to just noodle for a minute, is to make the point that when you have a function that isn't periodic, you can extend it, you can create a periodic version of that function, and then do all of this analysis on it. And you say, great, thanks a lot, Tim. How do I actually do this stupid analysis? Like, can you show me how to calculate these things? Yes, I absolutely can, and I will. And that will be the next video, will be the worked out example that shows you how to do one of these so you can see it in implementation. And of course, I have to talk about why it matters, because why wouldn't I? So with that, thank you for your patience. Yeah, I knew this one was going to run long. The next one, we're just going to get in there, do some math, and get out. So thanks for sticking with me, and I will show you that example real soon.